In this segment, we are going to look at how to conduct hypothesis tests in R, particularly as they relate to subgroup analysis. As an example, suppose we're working as an analyst for the Department of Education, and we're tasked with investigating a state representative's claim that enrollments are down. That is, fewer than 20,000 students are enrolled in state schools on average. And we're going to test this claim at a 95% confidence level. To recap how that translates to our alpha level, it would be 1 minus the confidence level as a decimal, 0.95, or an alpha level of 0.05, which we will return to later. Our null hypothesis given here, mu equal 20,000, that's stating that by default, we're assuming the true population mean is 20,000 students. The alternative hypothesis aligns with the claim which we are trying to test, mu less than 20,000. In other words, aligning with what we are testing, fewer than 20,000. Let's take a look at what the data looks like. This is taken from Hawk's learning dataset called Campus Crime, for which you see information about that in the first 2 columns. But we're interested in investigating total enrollment for this particular problem scenario. And notice in the information presented within R, this is a snapshot of the data. It shows a comma in the report of total enrollment, which indicates that this is being recognized in R as a character string or a word. So we want to convert that to a number and remove the comma. How do we do that in R? Take a look at that top line in our code. Total enrollment is going to be replaced with a numeric type variable. Coming from total enrollment, that's this third argument here. And we want it with the comma substituted with nothing, is what we're indicating there with that G sub function. So we're taking the comma out and replacing the information that's currently in that variable with just the number. And making R recognize it as a numeric variable type with that as numeric function. Then we'll take a look at the summary information, standard deviation, assess our normality related to enrollment as a variable with the histogram and QQ plot, and look at our results of a t-test with the true population mean set at 20,000 and alternative hypothesis formulated as less than, and a confidence level of 95%. Let's first take a look at the summary information and t-test results from R. Notice from the summary here that all of the schools in the data set have enrollment 14,600 on average. And the p-value from our t-test, 0.04, is less than the alpha level, 0.05, which would indicate we want to reject the null hypothesis based on this evidence. Now, how much confidence can we place in that conclusion that enrollments are less than 20,000 most likely in the population? That's what we are saying. If we reject the null and endorse or show that there was evidence to support the alternative as being plausible, we're saying that the state representative's claim is plausibly true. In other words, enrollment could be less than 20,000 on average. However, we have not yet taken a look at the assumption of normality. So let's look at those generated from the histogram and QQ norm functions. First, we have on the left the QQ plot, or normal probability plot, where we're looking for all of these points to be close to the line imposed on the graph. And you can see here, these are not. So that is an indication that the data is non-normal. Also in our histogram, notice that enrollments less than 5,000 are very frequent. There are 10 schools in the data set for which the enrollment is less than 5,000. All of the others fall in the range from 10,000 to 40,000, which is probably what aligns more so with the claim around 20,000. So what's going on with those other schools that have enrollment less than 5,000? We need to investigate that. Let's look back at the data. Notice for those with enrollment less than 5,000, we have another variable, private school. And by 1, in the place of that variable, it's indicating yes, this is a private school. Yes, this is a private school. All of the others with a 0 would be indicating no, it's not a private school. In other words, it's a public school. So the representative's claim is more aligned with enrollments at a public institution, since that is where we might expect enrollment to be around 20,000, or if they are in fact declining, perhaps less than 20,000. So to include these private schools in our analysis is distorting our result. In other words, it is diminishing the confidence we might place in our conclusion from that original t-test. So let's update our analysis so that we can be more confident in what we are concluding regarding this claim. Notice in our updated example, we are simply saying that this applies to public schools, the test that we are about to conduct. And to update our code so that we are only analyzing those schools which are public schools, notice in the summary function there at the top of our code, we have a call to the variable total enrollment, but with a condition as indicated by the bracketed information directly to the right of it. That is, total enrollment for which private schools must equal 0. In other words, it's not a private school. So that's translating to, okay, give us the data for enrollment, but only for those public schools. And you see that condition repeated all throughout our calls to total enrollment for this updated or revised analysis. Everywhere we are making a call to total enrollment, we have copied and pasted in there that condition that private school equals 0. Looking at the bottom of the screen at our normality diagnostics, the histogram appears to be more normally distributed. It's not perfect, but we no longer have that spike on the left, and this is starting to exhibit a more normal distribution, which is good information that allows you to place more confidence in whatever conclusions you draw from a hypothesis test. Also, in our QQ plot over here on the right, notice that the points are more in alignment in this graph. They're closer to the line imposed on the QQ plot, indicating the data is more normally distributed. So that's all good news as we move into interpreting our t-test. Let's take a look at that. Notice now the average of the sample of public schools is 26,000 roughly in enrollment. And the p-value associated with the test is now 0.96, greater than our alpha level, not less than 0.05. In other words, so we will not reject the null. Do not reject the null hypothesis. So the alternative hypothesis has been found not plausible in this case. Since the null hypothesis is not rejected, that means we think it is plausible that the true population mean enrollment among public schools would be roughly 20,000. There is insufficient evidence, in other words, to suggest that the average is less than 20,000 students. So let's summarize what we have found based on this t-test of a subgroup public schools. We found that the data for strictly public schools on enrollment was more normally distributed, and therefore that allows us to place more confidence in the results of our t-test, which suggests we should not reject the null hypothesis. That means we have insufficient evidence to support the representative's claim that enrollments are less than 20,000 on average.